Right. So today we'll start with solving actual three-dimensional fluid flow problems. So in the previous few lectures, we have talked about the stream function vorticity approach, which is quite effective because that helps us get rid of the pressure field. But the problem or the limitation with that approach is that it only works in two dimensions, because stream function by its definition is only available in two dimensions. You cannot define a stream function in three dimensions. Although there are alternate approaches where you use a velocity potential that only works for situations where you can define a velocity potential, that is your rotational flows. But in those situations, the equations actually become more complicated than what you would get in terms of solving fluid mechanics equations. So there's no point transforming from velocity components UVW and pressure to a stream function vorticity formulation, because in that case you get more number of variables. So you're basically complexifying the problem. Okay, so that's the main reason that we tend to go for actual fluid mechanics or fluid flow solvers, which solve for the primitive variables, that is U, V, W, and P. So we call these the primitive variables in fluid mechanics. Right, so let's write the equations again that we'll be solving. So the first one is the x momentum equation. And now to demonstrate the approach, I'll still be using two dimensions. Although this approach easily scales up to three dimensions, but it's difficult to draw control volumes in 3D and so on. So just to keep the work simple, I'll demonstrate this approach in 2D, but this works in 3D as well. So the equations we have is, the first is the x velocity equation or the u equation. So the velocity vector, in this case given as u vector, has components u, v, and w. In the previous lectures, I may have been using a v vector, but they mean the same thing. Okay. That's the velocity vector. So the first equation is the u equation. Call this 1. Then the v equation is simply replacing u scalar with a v. And the pressure derivative is in partial derivative of p with respect to y here. All right. So these are our x and y velocity equations. And we how many unknowns do we have in this situation? What are the unknowns here? U, V, W, and P. But in this case, we have U, V, and P because we're talking about a 2D problem. Okay, there's no W. So in the present discussion, we have three unknowns, U, V, and P. So where is the P equation? So there's one equation for U, one equation for V, as you can see. So where is the equation for pressure? Exactly. So we have an equation called the continuity equation. That's a mass conservation, which is an indirect way to specify, although that equation does not have any pressure in it, but still that gives us a system of three equations and three unknowns. Okay. So that the third one is the continuity equation. So we also call this continuity equation as a compatibility equation for the velocity field. So this word compatibility equation is used in the sense of mathematics than the physics. So let's try to understand this idea as to what it means by this compatibility equation. So let us say that we are trying to solve 1 and 2. So to solve 1 and 2, what I mean is that I am trying to solve for the component u from equation number 1 and the component v from equation number 2. But they include pressure as well. So what I can do is I can guess a pressure and put it there. But the chances are that that guess pressure will result in u and v that will not satisfy equation number 3. So let us now for this broad discussion, let us say that 1 and 2 are decoupled in the sense that I can solve for u from equation number 1 independently from equation number 2. Although they are coupled, you can see that there is a vector there. So u and v components appear in both equations, but there are ways to decouple them. So I can solve equation number 1 separately in a separate loop to solve for u, and I can use equation number 2 to solve for v. But to solve for that, I need a p. So what I do is I guess a pressure and put it there. Any p is a scalar field, so I can have any function of x and y. But the chances are that whatever u and v I get from equations number 1 and 2 will definitely not satisfy, or in most cases will not satisfy equation number 3. Equation number 3 is simply a compatibility. It's saying that del u by del x should be equal to minus del v by del y. So what are the chances? Very close to 0, right? Because I just guessed a pressure field. But if I keep guessing it and I have a way to improve my guess, then I can reach a stage where I can find the right pressure. And the way I figure out that I found the right pressure is that the solutions of 1 and 2 should satisfy equation number 3. Okay. Ultimately, we want a velocity field that satisfies equations 1 and 2 and 3, all three of them. Okay. So a feel for the approach that we'll be using is that we'll guess a pressure and we'll solve for u and v from equations 1 and 2 respectively. And then we will use equation number 3 to somehow improve our guess for pressure, so that we reach a stage where equation number 3, the right hand side actually becomes 0. That is, equation number 3 satisfies the divergence free velocity field, or del u by del x becomes equal to minus del v by del y. Okay. So for all this discussion, I'll just write that P has to be chosen, the pressure field P, which is a function of x, y and z, and T in fact could also be a function of time. So the pressure field P as a function of position vector x and t has to be chosen such that the solutions to equations 1 and 2, which is basically solving for u and v respectively, result in a divergence free velocity field. Divergence free means del dot u is equal to 0. So this equation number 3 actually is nothing but the divergence of the velocity field is equal to 0. So we call it divergence free velocity field because the divergence of velocity vector is 0. That is, it satisfies equation number 3. So that's basically the main idea of whatever we'll discuss in the next 5 to 8 lectures. We'll discuss different ways to solve these velocity equations. They'll get a bit intense, but the whole underlying idea is this. Is this clear? It's a very important idea. So if it's not clear, I'm happy to repeat it. Is this clear? Everyone? Okay. So let's dive into solving these equations. As usual, what we'll do is we'll start with an explicit approach because by now you may appreciate the fact that programming explicit approaches are much easier than implicit. Implicit, you have to write a linear system and then you have to define a matrix or you have to use iterative approaches to solve them. But explicit approaches are much easier. You have an unknown equal to all known quantities. And in fact, we discussed to find steady state solutions to equations, we tend to use something called false transients. So we add a del phi by del t term into the equation, even though the equation may be a steady state problem, like an elliptic problem. But we add del phi by del t and use an explicit approach till we reach a steady state. It's a very common way to use the idea of explicit approach because it's much easier to program explicit approach in general. Okay, so we'll start with explicit discussion and then we'll go to implicit approaches. Well, what is the meaning of using an explicit approach to solve the problem? So let's look at equation number 1 to start with. So we have a term del u by del t and then we have other terms which include the convection term. So this time let me expand this. So in explicit approach, what we do is we use something called a backward time and then we have other space discretization. This time I won't say center space because now we have both diffusion and convective terms. Convective terms are typically upwinded. So we'll not use BTCS, the word backward time center space, but we know the idea that for the transient term, we'll write this as un plus 1 minus un upon delta t. And for all other terms, we'll discretize them at nth time. So this superscript n basically means they are discretized at the nth time. Now, how we discretize them, that is something we'll worry later. In fact, we know more or less, but you can either use a finite difference or a finite volume technique. In fact, all the terms can be discretized in a separate way depending on which term dominates and so on, but that discussion will come a bit later. Although we have learned the individual parts, now we have to learn how to work with them if we have all the terms thrown together in the equation, like the diffusion term, source term and convection terms. But the main idea of explicit approach is that since all the terms other than this transient term are written at the nth time, so now I can easily write un plus 1 as a function of known values. Because if you see at these terms will include u and v at the nth time at different spatial points. Because I have discretized them at the nth time. But that is known because the whole idea is that you know the nth values and then you find the n plus 1th values. Right? Similarly, on the right hand side, since we would have known the nth time velocity and pressure values, so we know the pressure values as well for the nth time. To start with, it will be from 0, but initial conditions are always known, right? So we'll know the initial values and then we can find the n equal to 1 values, n equal to 2 values and so on. Okay. So this is the explicit approach. Is that clear? So this is equation. So since we are calling equation number 1, so we'll call it 1a. So a stands for It's a modified form of equation number 1. Equation number 1 was just the equation. This is discretized form, semi-discretized form, because we still haven't discretized the other terms except the transient term, but we get the idea. So let's look at the V equation now. It's very similar. At the nth time, similarly the second term is also at the nth time. And all other terms also at the discretized at the nth time. Okay, since we know the velocity and pressure values at the nth time, we can use equations 1a and 2a to find un plus 1 and vn plus 1. So now you can understand what I meant with saying that equation 1a is used to get the x velocity, that is u, and equation 2a is used for getting the y velocity, that is v, at the n plus 1th time. But there is a problem. Can you guess the problem? Pn is known. Pn is known from the previous time. There is a problem with the solution that we have just found out. Un plus 1 and Vn plus 1. They will have some problem. Can you identify that problem? Exactly. That may not satisfy continuity. Why should it satisfy continuity? Because it is using a pressure from the previous time, right? So un plus 1 and Vn plus 1 in most cases will not satisfy. Unless the pressure does not change with time, it will not satisfy continuity. We'll say that this may not be equal to 0. With the choice of Pn. So now we propose, so this is how actual research thinking works as well. So we are thinking in a certain way. We started with an explicit approach, that is typically how it works, but we did find that there is a problem, that is equation number 3, continuity equation, is not satisfied with this, or may not be, in most cases will not be satisfied with this approach. But let us say, if somehow we were lucky enough that we knew Pn plus 1, then things would be fine. So if instead of this, I knew the actual pressure, that's the whole idea, right? If you knew the pressure, you substitute the correct pressure That's what we discussed in the previous page. That if you substitute the correct pressure field, whatever way you, I mean, how you find out, that is of course a different problem. But let us say you could find the right pressure field, and the right pressure field here means the pressure at the n plus 1th time, because we're trying to solve, or we're trying to satisfy the continuity at the n plus 1th time. So to be able to find the correct velocities at n plus 1th time, if we substitute the correct pressure at that time, then continuity should be satisfied with the solution. Agreed? That's the whole problem, to find the pressure. So the right pressure here means pressure at n plus 1th time. So if we could do it, I'll erase that because that will confuse you later. It's better to write these equations again. But if we can discretize P at the n plus 1th time in these equations, then continuity will be satisfied. Okay, so I'll propose a solution, and then we'll figure out how to use that proposal to develop a method. Of course, if you discretize P at the n plus 1th time, then you have another unknown. Because in addition to un plus 1, you also have now Pn plus 1. Because if you had Pn, then they were known from the previous time step. But Pn plus 1 has to be found out. So now what we do is, since Pn plus 1 has to be found out, we'll include the continuity equation as well in the equation, in the system. So we cannot solve 1a and 2a together. We'll solve this modified version. I'll call it 1b and 2b. Okay. So let's write 1b. Let me see if I can just copy it here. It's much easier if I just write it again. I think it will be okay if I write the compact form. The difference is this is at the n plus 1th time, the pressure gradient, but everything else stays as it is. We'll call this 1b and this is 2b. So they're following similar numbering, that 1 is for the u equation and 2 is for the v equation, except that we are calling it b because this is pressure gradient at the n plus 1th time. Okay, so this cannot be solved using an explicit approach directly. So what we'll do now is we will use, or we will solve 1b. I cannot say 1b and 2b to get un plus 1 and bn plus 1 because I need to find Pn plus 1 as well. So I'll include the equation number 3, which was continuity equation, to find Un plus 1, Vn plus 1 and Pn plus 1. Just a name. Okay? Don't get stuck with it. This approach is called a semi-explicit approach or semi-explicit scheme. We are calling it semi-explicit because we'll have other schemes which will be different from this, so they'll have to be given a different name. It's called semi-explicit because for U and V, you have a purely explicit approach that you write Un plus 1 and Vn plus 1 in terms of velocities at the nth time. But for pressure, you are discretizing at the n plus 1th time only. So it's sort of implicit pressure. Okay? It's just a name, so don't get bothered with it. But this is the name for this approach. So now the question is, how do we combine 1V and 2B with equation number 3 to get an algorithm? Because still we do not know how to find Pn plus 1s from here. So I'm not writing the equations again. So this is 1b, 2b and 3. So this is the system that we are going to solve with this algorithm that we are proposing. This algorithm has a name in literature. It's called SMAC. So you'll see these words in commercial and open source codes. When you're trying to choose the right solver, it'll be either SMAC, simple, simpler, and so on. So these are just acronyms. Okay? So SMAC, simplified marker and cell scheme, or the algorithm, is the one that we are going to discuss now. This algorithm is an algorithm that is used to solve the system 1b, 2b, and continuity, that is equation number 3. So whatever comes next is going to be the second major idea of today's discussion. Now we are getting very intense in terms of the idea in CFDs, in ideas in CFD. Okay, we have learned all the basic methods and so on, but this lecture is going to be quite intense in terms of the ideas. The first idea was that we have to somehow figure out the right pressure. So if we can figure out a way to find the right pressure field and substitute that into equations 1 and 2, we can find the velocities. Right now we're doing it explicitly, we can also do it implicitly. That's the first idea. The second idea is, it's not specific to this SMAC method, it's quite general. In fact, it's used in finite difference, finite element, finite volume. It's used, it's a very common approach. In fact, most of the methods use this idea. It's called a predictor corrector approach. So I'll put idea 2, and the first idea was this idea of finding the right pressure. because things are getting intense, so I don't want you to be get lost in the equations and not understand, because see, equations can be understood later also, but these ideas are what are particularly important to be discussed in this kind of a discussion in a classroom. So if after 5 or 10 years you work in CFD or you work in some sort of computational mechanics field, you only remember these ideas. That's good enough. So every lecture typically has one idea, but this one has two major ideas. So I'm trying to highlight them. So predictor corrector approach. So what it means is you solve the equations in two steps: a predictor step and a corrector step. So let's write these steps. So I'll discuss this in the context of SMAC scheme, but the idea is very general. You will see the idea appear again and again in all schemes. But for discussion, to make things simpler to understand, this discussion right now will be in the sense in the context of the SMAC scheme. So step 1 is to predict some velocities. They are not the correct velocities. They are not the un plus 1 and vn plus 1. So they are some intermediate predicted velocities. So we'll call predict intermediate using equations for u and v velocities. So since we are not using 1b and 2b, because if we used 1b and 2b, we would find un plus 1 and vn plus 1, because 1b is for un plus 1 and 2b is for vn plus 1. Okay, so I'll not use 1b and 2b. I'll say just in general that so you have equations for u and v. I'll write those equations to predict intermediate velocities. And the second step is to correct them. Now you may have guessed that since we are predicting some intermediate velocity, that intermediate velocity will not satisfy continuity equation. So now we'll correct them. So we'll add something to it. Now that added term may be positive or negative, that doesn't matter. But we'll have to correct those predicted values using the continuity equation, so that the continuity equation is satisfied. So you correct the intermediate velocities using, this time I can say, continuity equation. So without repeating this, I'll show you how we do it in the SMAC scheme, so that it reinforces the idea. Okay, so this is the approach. So we are now applying it to step 1, which is called the predictor step. So since it's an intermediate velocity, I'll not use un plus 1, I'll call it a u star. So please focus on how this equation is going to be different from equation 1b. 1b. So 1b was this equation where you had an explicit approach, but you had pressures at n plus 1. Okay, that's the semi-explicit system that we are solving. So try to figure out how this equation is going to be different from that. So how are 1C and 2C different from 1B and 2B? The pressure term is at nth. So this is basically 1A and 2A, right? So we started with this idea, explicit, completely explicit. Even the pressure was at nth time. But then we said the problem is that it will not satisfy continuity. So that is the reason we are not calling it un plus 1 and vn plus 1. We are calling it u star and v star. I could have called it 1A and 2A, but to keep things simple in the order, I will call it 1C and 2C because I have a star here, not n plus 1. There's a difference. Now this can be solved because at the nth time, all it needs is the velocities and pressure at the nth time to get u star and v star. Okay. So this can easily be solved. So that was step number 1. So step number 1 done. This is called predictor step. The corrector step, it said that now we have to correct the intermediate velocities or the predicted velocities using continuity equation. So now we have to figure out a way, and now this is the actual the equations 1C and 2C are very easy to solve. They don't take much computational time as well. It's the step number 2 that is going to be a major work in this algorithm in terms of proposing the algorithm as well as in terms of computational time as well. So it will take some space to discuss step number 2. So it's not just straightforward to write it. So first what I'll do is I'll subtract 1C and 2C from 1B and 2B. The difference between 1C and 1B is that in 1C that's available here, the pressure gradient is at nth time. And in 1B, the pressure was at n plus 1th time. But also in 1B, on the left hand side, you had un plus 1. And in 1C, you had u star. So what I'll do now is I'll say subtract 1C from 1B. I won't do it because most of the terms, convective and diffusive terms will simply vanish. So the difference will be between un plus 1 minus u star upon delta t. And then on the right hand side, we have minus 1 by rho times del by del x of Pn plus 1 minus Pn. So these are simply intermediate equations. We are not solving these equations. So I have to give some labels to this. I'll call it small a and small b for these intermediate equations because I might need them for discussion. Is this clear? So for discussion, we'll define some terms. The first one is u prime, which is, so it's a definition, so I'll have 3 lines here instead of 2, which is un plus 1 minus u star. Similarly, I'll define v prime, which is vn plus 1 minus v star. I'll need this in equations just to keep things simple. I'll use u prime and v prime rather than using the term un plus 1 minus u star again and again. And we'll also define a term p prime, which is pn plus 1 minus pn. And we'll call them some names because I don't want to use u prime and v prime in discussion. So I'll call u prime as velocity correction, u prime and v prime as the correction for x and y velocities. So these two terms are called, so write it on the left hand side. velocity correction, and this one is called pressure correction. So in step number 1, we found out u star and v star. So if I knew u prime, I simply have to add u prime to u star to get un plus 1, because u prime is simply the difference of un plus 1 and u star. So if I knew u prime, or if I could find u prime, I will add u prime to u star to get un plus 1. Similarly, if I am able to find v prime, I can add v prime to v star to get vn plus 1. And if I know p prime, I can add p prime to pn. There's no p star. The gas pressure is at the nth time. That's what we are using. So if I know p prime, or if I could find p prime, I'll add p prime to pn to get pn plus 1. Right? So now the problem boils down to finding u prime, v prime and p prime. So let's explicitly write u prime expressions using small a and small b. So u prime using small a is minus delta t upon rho times del by del x of p prime. So this we call a1, because it's small a but modified slightly. Then we have v prime using equation small b as minus delta t upon rho times del by del y of p prime, which is b1. Have we used the continuity equation yet?
No,
So now is the time to use it. Okay. So the continuity equation is del by del x of un plus 1. Remember, we are trying to satisfy continuity for the n plus 1th velocities, because nth velocities, if they were correct, they already satisfy that. We already know them. We're trying to find n plus 1th velocity, so we have to ensure the continuity for that velocity. So del by del x of un plus 1 plus del by del y of vn plus 1 has to be 0. So now what I'll do is, for un plus 1, I'll write un plus 1 as un plus, u star plus u prime, and for vn plus 1 is v star plus v prime, and that is equal to 0. So this gives us del by del x of u prime plus del by del y of v prime is equal to minus the divergence of the starred velocity. The reason I have used the del dot u star on the right hand side, because u star is known. In step number 1, we calculated u star's values. Okay, so the right hand side is usually the known values, left hand side is the unknown values you're trying to find. So this is known from step 1. Almost there, just 2 more minutes. Now we'll use A1 and B1. So use A1 and B1 in above. So for u prime, we have to substitute minus delta t by rho del p prime by del x. So this becomes del 2 p prime by del x2, and then from del v prime by del y, we will get a del 2 p prime by del y2, and this is equal to, I have moved the delta t by rho term on the right hand side with the negative sign. So this becomes rho by delta t times the divergence of u star. Well, that's it. Can we solve this equation? Well, you know how to solve this. This is an elliptic equation. Laplace's equation has 0 on the right hand side. This one has a non-zero term on the right hand side. So it's del 2 phi by del x2 plus del 2 phi by del y2 is equal to some source term s. We have solved this. If you go back to your notes, we have solved this equation. So on the right hand side, we have a known value. You know rho, you know delta t, and you know divergence of u star, because u star we have found from step number 1. So we know the u star and u star vector. So we know u star and v star values everywhere. So we simply have to substitute those and solve this equation. So this is intermediate values, not assumed values. Assume is something you assume, but you are solving for u star and v star in step number 1. Okay. So when you solve this equation, what do you get? You get p prime. You get p prime everywhere. So from there, can we find u prime and v prime?
Yes.
Well, equations a1 and b1. If you know p prime everywhere, you can find del p prime by del x also, discretize them. So you get u prime and v prime. So corrector step has, the first step is to solve this equation, and that takes a lot of time. So now we'll summarize the corrector step. So this is called corrector step. Okay, the above equation is called the corrector equation, or we simply call it Poisson equation for pressure correction. So the first thing you have to do is you have to compute del dot u star, because you know only u star velocities from step 1. You don't know del dot u star. So you compute that. Then, so compute means using u star vector you find del dot u star. It's easy to find. And then we solve this pressure Poisson equation, which is the Laplacian of p prime is equal to rho upon delta t times del dot u star vector. Now with appropriate boundary conditions. So we'll discuss these boundary conditions later. You could use any iterative method. Let's say you use the Gauss-Seidel successive over relaxation, or you could use a false transient approach by adding a del p prime by del t and solve it using explicit approach, whatever you want. By now you know all those approaches from your lab experiences and assignment experiences. Okay, so you solve this equation for p prime, and then step number 3 is to compute. So there's a difference between compute and solve. Okay, solve is when you solve the equation. Compute is you use values to find some other values. So you compute u prime, which is minus delta t upon rho times del p prime by del x, and v prime and then finally, what do we do finally? You have to find un plus 1 and vn plus 1. That's the whole aim. Right? So you find un plus 1 as u star plus u prime. You find vn plus 1, or you compute vn plus 1 as v star plus v prime, and also pn plus 1 as pn plus p prime. Alright, so it was a pretty intense lecture. with two major ideas. The first one being the pressure has to be found out somehow, and if you can find the right pressure, then you find the un plus 1 and vn plus 1, which are satisfying continuity equation. And the second one was the idea of the predictor corrector approach, where to implement this idea, because you just cannot find it directly. So this is a way to implement idea 1. So the idea 2 is you predict velocities and then you correct them using continuity equation. So we'll stop here now, and I'll see you tomorrow morning to discuss further from here.
Basically, we are predicting all u, v, and